Okay. All right. Flying blind a little bit here, but we'll figure something out. So get this out of the way. Again, I'm still an employee at Columbia University. I'm still a co-founder of Stan Group, which is a private company doing stuff with businesses involving Stan. According to Columbia University policy, those two things together require those facts to be disclosed in every presentation. For those of you who were at the QMSS thing last Wednesday, Eric is another co-founder of Stan Group, talking to you about the importance of generative models and Bayesian inference. We'll get into that a little bit today, although Eric is not a co-founder of Columbia, so he was not in violation of any rule by talking to you. So the goals for the class today are to start applying the Bayesian machinery. We're still not in a position to apply this to any kind of interesting problems, because all interesting problems essentially require that we learn how to draw random values from posterior distributions, which we'll start to learn about next week. So this week, we're still restricted to posterior distributions that we can manage algebraically, or maybe one parameter models, and we can do the denominator of Bayes' rule with numerical integration, even if we can't solve it explicitly. But we want to start to apply the process of doing Bayesian inference and to start thinking about situations in which it could apply. So today we want to answer a question like, what do you believe is the average number of points for a team to score in the Super Bowl? And people are interested in questions about that. We want to keep emphasizing this idea of a predictive distribution, the distribution that you believe the future data to be conditional on past data, etc. So we want to keep emphasizing that because it's a very important and powerful aspect of Bayesian inference. And then finally, not really a goal for the class, but just announcement. So I'm going to continue to have office hours Monday afternoon. But if that's not convenient for you to make it on campus, I'm happy to do office hours online, either in those same time slots, or if those time slots don't work for you, at a different time. But if you want to sign up for one of the slots, but you don't actually want to come to the basement to see me in my office, just put a comment. Like when you sign up for office hours on CourseWorks, there's like a little box where you can put a comment. People typically ramble on about all the stuff they don't understand. Don't do that. Just say I would prefer to do online office hours, and we'll set that up. But I'd say most of the time I will physically be in my office if you prefer that, or even if you don't. Okay, questions. Questions from last week before that. Homework? Anything? Nope. We all here? Not quite. Now we're all here. Let's do it. Okay, so just to kind of recap a little bit and to tie this to the reading. So Krushke in his book says that Bayesian inference is basically possibilities, or models are possibilities over which we allocate credibility, our parameter values in meaningful mathematical models. So you need to set up a meaningful mathematical model for the data generating process that you're interested in studying. That meaningful mathematical model will typically have one or usually more parameters, which we'll call theta. Theta could be a vector. And you want to make inference about those parameter values, and possibly inferences about functions of those parameter values, such as the expectation operator. But you need to, condition on the data to update your beliefs about what those parameter values are. And these possibilities, they're represented by the sample space, omega. That's usually going to be a continuous sample space if we're talking about parameters, theta. And so those are the parameters. And you have some model for the data generating process for the outcome that you're interested in. And all that, like we talked about before, leads to Bayes' rule. You have a posterior PDF for the parameters conditional on the data is equal to a prior PDF for the parameters not conditional on the new data. That could condition on old data. So you can use a posterior distribution that you got yesterday for your prior distribution on the parameters that you believe today when you're anticipating getting more data tomorrow, and then you're going to update your beliefs again. So that's the first term there. The second term is what we've been calling a PDF or a PMF for the outcome data that you're interested, Y, conditional on theta. Now, oftentimes there's also going to be X as well, but we often don't really write the X because everything is sort of conditional on the X, whereas we're thinking of Y as the outcome variable. Similarly, if there are hyperparameter values like mu and sigma or whatever, if you're specifying a normal prior, and technically theta is conditional on mu and sigma, but you supply mu and sigma, like you know what they are. So all of this is going to be conditional on everything that's known, and it becomes sort of tedious to write out everything that's known. So we're just going to focus on the things that at one or more point in time might be unknown, such as Y if you haven't collected the data yet. So in that case, we have a PDF or a PMF for Y conditional on theta, and that's those things together constitute a joint PDF between Y and theta. That's for the numerator of Bayes' rule. And then in the denominator of Bayes' rule, we have a marginal probability mass or density function for the data that does not involve theta at all. And that's because the denominator is merely the integral of the numerator, integrating over the sample space omega, integrating away or out or purging theta. So that integral is going to be a definite integral, and then you're going to evaluate it at the upper limit of omega and subtract it at the lower limit of omega. And by putting in, those two values for theta, the upper and lower limit of omega, you're getting a function, or really more just a number for that area that does not involve theta. It only depends on the data that you actually have in your hands, Y. And that's an important point about Bayesian inference, is it's conditional on the data that you have in your hands and doesn't involve anything else, like data that you haven't collected yet or repeated samples from the population that you're not actually doing. There's none of that comes into play. Questions? No. Krushke goes on to say that Bayesian inference is reallocation of credibility or reallocation of your beliefs across possibilities. So you come in believing something, which is represented by the prior PDF for theta. You get some data, you condition on that data and that data alone, and you get updated beliefs about what theta is, the left-hand side of Bayes' rule, the posterior PDF. And that process involves reallocation, shifting the prior PDF around into the posterior PDF. It's usually going to become more concentrated when you do that. And that's the whole idea of Bayesian inference. So you have these beliefs that's represented by f of theta. You multiply by f of y given theta and divide by f of y. And that transforms your prior PDF into your posterior PDF. And then you can do anything you want with that posterior PDF. Take its expectation, its median, its CDF, evaluate it at various places. You can use it to predict future data. You can use it to make decisions because it represents the sort of complete state of beliefs that you have about theta, bringing together what you believed, before you did the data analysis and the data. So that's all you really can believe at that point in time until you get even more data, and then you can update yourself again. All right? So that's the basic idea of Bayesian inference as opposed to just all these kind of manipulations of probability distributions that we've been doing before when sort of saying like you need to learn how to do this in order to do Bayesian inference. Questions? Yes?
Can we say data, why do we mean the dependent variable or?
Yes. So by data and y, I mean pretty much the same thing. There could very well be x. So this could be y conditional on theta and x, but x is considered known. That's what you're always conditioning everything on. So it's hard to fit on the slide if you write theta and like mu and sigma when you are supplying mu and sigma. So it's known. Yeah, we only need to like keep track of unknown things.
Okay, so basically we consider x as a constant.
Yeah. Yeah. All right. Good. Okay. So slight amendment to what I said before, we need to talk about the likelihood function. This is really just making what might seem a kind of narrow distinction. So a likelihood function is mathematically speaking just a PDF or a PMF, which we've been talking about repeatedly over the past few weeks, but there's three distinctions. First is a real PDF or a PMF, so sort of f of x, x conditional on theta, we're thinking of x as the random variable. That's why I somewhat redundantly write x after the f. To emphasize with that notation, we're thinking about x as being a random variable. Consequently, that thing will integrate or sum to 1 over the sample space of x. However, if we say we're talking about a likelihood function, it's mathematically the same thing, except we're considering x to be given, like we have data on it, and theta to be the unknown thing. And this likelihood function, which I'll denote by L and then theta semicolon x, we're thinking that as a function of theta. But if you take the likelihood function and integrate it over the sample space of theta, so what I've done here, like if theta is a vector, then you're going to have to integrate it k times or whatever. That does not integrate to 1. It'll be some positive number. It's not important what it is. We never actually do it, but it's not 1. So these functions, they integrate to 1 or sum to 1 over the random variable in question. But if we're saying, okay, x is not a random variable once we've collected data on it, we're just interested in like this x, this y, whatever. Then this same function is now a function of theta, but it doesn't have the same properties as a PMF or a PDF does as a function of theta, in the sense it doesn't integrate to 1 or anything like that. So for a given value of the data, a PMF or a PDF becomes a likelihood function, and we worry about the theta part, which we don't actually know. But in sort of the traditional notation, we're saying this is the PMF or PDF of x given theta, as if theta was actually given to us. But that's just a hypothetical. In every serious application, we're going to have to go about estimating theta, so it's not really given anymore, and we consider the likelihood function to be a function of theta. Second distinction, when someone says the likelihood function, they usually mean for an entire sample of n observations that you've collected data on, rather than the likelihood function for one observation. Sometimes we'll talk about it for one observation, but if I just say the likelihood function, I mean for an entire sample of conditionally independent observations, conditional on theta. Consequently, the likelihood for the whole sample is the product of the likelihood functions for each observation. That's usually what people mean when they say the likelihood function for the whole sample. But it's a function of theta. We're evaluating at possible values of theta, plugging in the data that we actually have collected. Yes?
How do you use that semicolon?
Semicolon.
Like theta and x?
Yeah, I usually just say the likelihood function of theta or at theta. If you're saying likelihood function, implicitly you have data. Otherwise, you wouldn't be talking about a likelihood function. So whatever the data are, they appear, but you're not interested in evaluating this likelihood function for any value of x except the x's that you have in your data set. Third distinction, by the likelihood function, we often mean the natural logarithm of what I just said the likelihood function is. That's technically known as the log likelihood function, but people oftentimes just leave off the log part even when they mean the logarithm of the likelihood function. And so if the likelihood function with capital L is the product of all these conditional independent contributions to the likelihood, the logarithm of the likelihood is the sum of the logarithms of each observation's contribution to the likelihood. So particularly when we do this empirically, it's always going to involve the logarithm of the likelihood. And that's okay because the logarithm is a monotonic function. So it doesn't really change the order of, anything like that. So there's a one-to-one, relation. Anything we can do with the log likelihood function implies the same thing with the likelihood function. Numerically speaking, log likelihood function is preferable for some of the reasons I started to get into on the homework in terms of not multiplying a whole bunch of tiny numbers together. But just sort of keep that in mind. I'll try to say log likelihood when I mean log likelihood, but after this week, I very rarely mean the not log likelihood. All right?
So the likelihood is like used only when you're estimating, really.
Yeah.
And not really in inference that much.
Yeah. You can talk about a PDF for X before you get the X, like X is coming in the mail tomorrow.
Right.
But if X came in the mail today, then you have it, and you're conditioning on it. Yes.
Was it clear for me why we use a natural logarithm of the likelihood?
It shouldn't be that clear yet. Numerically, it's preferable. You don't want to be multiplying a lot of tiny numbers together because the computer is eventually just going to call that 0. And then it can't go on anymore because 0 multiplied by anything is 0. Technically speaking, the product of a bunch of small numbers is something slightly bigger than 0, but it gets to a point where a computer can't handle it. So what you'd rather do is sum up the logarithm of a bunch of tiny numbers, which is like a big-ish negative number. And computers can add big negative numbers all day. All right. Questions about likelihood function? Okay, so you can't see the code for this, but when I put it up on Courseworks, you'll see the R code that makes this slider thing. This is the CDF for what's known as the gamma distribution. So for some random variable, it's going to have 2 parameters, the shape and the rate. And here we have the CDF for the gamma distribution with shape of 1 and rate of 1. But if I can work the mouse, I can slide these around to get different shapes. So that makes like a steeper CDF. I can slide it back. I can get like a shallower CDF, etc. I can grab the other one and I could shift it over and get more of like a S shape. So, if you're thinking about this random variable, which at this point has like no context to it, so it's hard to think about, you can always make yourself one of these plots, these like slidey plots, to figure out, okay, what seems like a reasonable CDF for my beliefs by turning the shape and the rate to be, whatever you want. So this is for a random variable that is non-negative. So that's start of a piece of information. It's a CDF. So you're saying things like the probability that it's less than or equal to 5 is like 0.58. Does that seem reasonable? And so overall for the whole shape of the curve, does that sort of correspond to a CDF that seems roughly reasonable to you, for this random variable that you don't know? At the same time, you don't want to sweat the details of this too much. You just want to get a shape that looks, plausible, and that's going to be good enough, okay? But one thing to notice about this is that if I go back to where it was originally, if I can work the mouse, come on, Heisenberg problem here. Ha! All right, help me out. Is that 1? That's 1.2. Scoot over. 1. Awesome. And I grab this one and scoot it all the way to 0. Then this line becomes flat. This is what's known as improper. So technically, the shape and the rate have to both be positive. But in the limit, as the rate goes to 0, it's still like positive, but it's approaching 0. And we get a CDF that is just, completely flat. And the PDF, the derivative of that is 0. So this is loosely speaking saying every positive number is equally likely. And by every positive number, I mean even numbers that go past the screen here. So beyond 20 to like 20 trillion. Like bigger than any number that can fit on your computer, or bigger than the number of atoms in the universe. All positive numbers essentially have equal chance under a prior like that. So this is what's sometimes known as uninformative prior, or what I tend to call uninformed prior. But you'll see a lot of people trying to use stuff like this, and you'll see the code when you get the notes later, and you can play around with your own. All right. So this is sort of different shapes that the gamma CDF can take. Yes.
When you said they all have equal likelihood, they all have the probability of 0, right?
Yes, but it's like equal probability of 0 in the sort of limiting sense. Yeah. Okay. So moving on to the PDF, we actually can't write the CDF of the gamma in an interesting or useful form, but the computer can evaluate it numerically pretty easily. So like I said, sample space is all positive numbers. We have alpha greater than 0. So this is what's known as the unit gamma distribution, or PDF of the unit gamma distribution. 1 over the gamma function evaluated at alpha times x, which is the random variable, to the power alpha minus 1, times e raised to the power of negative x, right? So if that's the case, what is an expression for the gamma function at alpha?
Alpha minus 1, gamma, alpha minus 1, or alpha minus 1.
So if alpha is an integer, then yes, this can be written in terms of a factorial function. But let's say alpha is not an integer. It's a positive real number.
Alpha minus 1, gamma, alpha minus 1.
Alpha minus 1.
Times gamma.
Yeah. There's also a relationship between the recursion of the alpha. In terms of the stuff that is written on the top of this slide, what is the expression for the gamma function evaluated at alpha for this PDF?
What do you mean by the unit gamma distribution?
That'll become clear later. That's not part of the answer. Any expression for the gamma function.
X alpha minus 1 minus x over fx.
Over fx? Oh, you mean put this in the numerator? No, that does not count. So x is, its sample space is all positive real numbers. It's continuous. Yes?
So we should integral that PDF to 1 and to calculate the alpha.
Correct. Thank you. Since this is a PDF, it integrates to 1 over x. Consequently, whatever that thing, the kernel there, integrates to, we divide by that thing, and now the PDF integrates to 1 over x. And so whatever that integrates to is in the denominator here. So an expression for the gamma function evaluated at alpha is the integral of the kernel over the sample space of x. All right, PDFs integrate to 1. So yeah, the computer can calculate gamma for you, but I can't even write it, and no one can, in a generally useful form. Okay? So more practice. Suppose the random variable t is a function of x. In particular, it's the function of x divided by beta, where beta is a positive number. What is the PDF of the random variable t? And how would we go about arriving at such a PDF?
dfx is a CDF.
T is a random variable. So it's just equal to x over beta. Beta is known to be positive. It's a constant, and x is a random variable itself with a unit gamma distribution. I like that start. X as a function of t is simply beta times t, right? Okay, we're going to need to know that. What else are we going to need to know about x as a function of t?
We find x is equal to beta t, we plug it into the PDF of x.
So we want to plug in not x, but what x is equal to in terms of t into that PDF there. And then the last step is to
Multiply it by the derivative of t with respect to x.
no.
Once you have the CDF, you do the transform thing. Right?
Yes, doing the transform thing. So we're going to evaluate that PDF in terms of t and multiply by the derivative of t with respect, derivative of x with respect to t, which is beta. So we do all that, and we get an expression for the general gamma distribution that appears on the right there. So unit gamma is a special case of general gamma when beta is equal to 1. So in the previous thing, alpha is the shape and beta is the rate. Just using Greek letters here. So unit gamma basically means beta is equal to 1. All right. So that's the PDF of the general gamma. It has shape alpha, rate beta. Those are both positive. Sometimes you'll see it written with a different parameterization using theta is equal to 1 over beta. It's pretty much the same thing, but with that substitution. And if you substitute out beta, theta is known as a scale parameter. So the rate parameter and the scale parameter are reciprocals of each other. You can use one, you can use the other. It's really just a question of what's the most mathematically convenient. Remember, in this scenario, you're supplying beta and supplying alpha. So you could supply theta for all you want and then just take the reciprocal of it and you have beta. The expectation of a general gamma variate is alpha over beta, or equivalently alpha times theta. So, fun fact about the gamma distribution. Questions about how we arrived at that with this transformation process. Hopefully we should get more comfortable now that we've done like 6 examples of that. We're going to do more, but we ought to be more comfortable with it already. Questions? Okay. So prior predicted distribution. So suppose you're going to observe n counts for your outcome, would you believe to be distributed Poisson with expectation mu, but you don't know what mu is. What is the PDF of observing such data? So that is going to be the PDF for Poisson, but we have n independent observations. So it's going to be the product of all that. And since it's the product of a bunch of things involving mu raised to the power of yi, we can write that instead as e raised to the power negative n times mu raised to the power sum of y's. And then there's the product from 1 to I equals 1 to n of yi factorial. So this is just the Poisson PMF. It should say PMF rather than PDF. But PMF for the case where we have n observations. It gets all multiplied together, okay? This is before we see the data yet. So what do you anticipate, what distribution do you anticipate the data to be distributed as? Anyone?
It's exponential in general, right? The exponential families.
Poisson is in the exponential family, yes. But the exponential is only one member of the exponential family. And we haven't really talked about the exponential yet, but it's a special case of the gamma with alpha equal 1 and beta equal 1. Or no, just alpha can be anything, beta has to be 1. So unit, gamma, and exponential are the same. Okay, but exponential, no, is not the right answer. What distribution do you anticipate the data to be? Wrong. Poisson conditional on mu, but you don't know what mu is. So you have to express your prior beliefs about mu in order to figure out what the distribution you anticipate for the data to look like. So this Poisson is the correct answer to what is the conditional PMF. What are your beliefs conditional on mu? Like if someone told you mu, then Poisson would be the right answer. But you don't know mu. That's what we're going to be trying to figure out. And so you have to allow your uncertainty about mu, which is represented by your prior. In this case, it's about to be a gamma prior for mu, to propagate over to your uncertainty as to what the data will look like. And this is what's known as the prior predictive distribution. If we use a gamma prior with shape alpha and rate beta for mu, yes.
Well, do we use gamma because it'll give us a conjugate?
Yes. That's why. So conjugate gamma prior with alpha and beta, you pick alpha and beta. We get a prior predictive distribution for the outcome y by multiplying our Poisson PMF for a single observation, let's say, that's given by this, by a gamma prior, which this is the PDF from the previous page, on mu, and then integrate mu from 0 to infinity, which are the possible values that mu could take. All this stuff that does not involve mu can go to the outside of the integral. And then we look at that expression, e raised to the power something involving mu, mu raised to the power something involving y and alpha. What does that integral come out to? What does that kernel there almost look like? Gamma function. So here we've changed it. It used to be e just raised to the negative of the random variable. Now we have e raised to the negative of the random variable times beta plus 1. And then there was random variable raised to the alpha minus 1. And now we have random variable raised to the y plus alpha minus 1. So that integral is another gamma function, and it's going to be equal to beta minus 1 raised to the power negative y plus alpha times the gamma function evaluated at y plus alpha. You get better at recognizing these patterns. Also, the gamma function, as was mentioned, if you're evaluating it at an integer, then it's equivalent to a factorial function if you shift it over by 1. So we put all those two things, or several things together, and let's also make a substitution that p is equal to 1 over beta plus 1. We get a prior predictive distribution for what we think a single observation will be distributed as, conditional not on mu, because we purged mu, conditional only on alpha and p, where p is a simple function of beta. And it's going to have this expression here, a bunch of gamma functions to the left, p raised to the power y times 1 minus p raised to the power alpha. And this is known as the p, again, that should be PMF, not PDF, of the so-called negative binomial distribution, which has a R function, built in to evaluate that density. Negative binomial distribution is one of the most frustrating because it has so many different parameterizations. But one way in which it can be obtained is by compounding a gamma prior for mu with a Poisson PMF for data given mu and purging out the mu. So you get a joint distribution of y and mu, and then you want to look just at the margin involving y. You integrate out the variable you don't want anymore. In this case, it's doable in the sense it just involves gamma functions, and there's a numerical implementation of the gamma function in R and every other computer language. All right? Yes?
I think to know the mu, but why do we choose gamma distribution to generate it?
Because it gave me an integral that I could do, as opposed to an integral that I can't do. Like no way, no how. There's no function in R that's been written to do it for me. So it would just be like little rectangles or something. That'd be the only way I could do the integral. I wouldn't have a mathematical form, but this is considered to be a mathematical form, even though it involves this gamma function that you can't write in a mathematical form, except as the integral of that kernel.
So we don't choose up like other distributions, just gamma distribution for every problem set?
Oh, no, not every problem set, just maybe one more problem set. But the gamma distribution is the only prior that you can put on the mu in a Poisson if you think your data are conditionally Poisson to get a doable analytical result. Any other prior that wasn't gamma, and you wouldn't have an analytical result. So I'm still cooking up these problems to not have to do random number simulation. I can just do math. All right.
That y in the prior predictor, the y there is the unknown, right?
Yes. So this is future data. So if I asked you how many points do you think, one of the teams from the Super Bowl, next year's Super Bowl? It hasn't happened yet.
So that would be a function of y, the alpha and the theta only.
Yes. So you could use that negative binomial to say what's the probability that a team scores 17 points in the Super Bowl. You put in 17 for y, you have your alpha and beta or p, whichever way you want to write it. And you could come up with the probability, your beliefs as to the probability a team would score 17 points in the Super Bowl.
Let's say you wanted to do like your bowling problem for one moment.
Okay.
You want to predict the problem on that. So let's say you use from the homework, like you have the gamma distribution as your or the Poisson, something that then makes well with the Fibonacci. So how do you go about that?
So how you go about that, it's actually extremely easy, even if you can't write the predictive distribution in an analytical form. All you have to do is take a large number of simulations. So in this case, I'm going to do alpha equals 40, beta equals 2. It's my hyperparameter values. And you draw from a Poisson, where we're going to do a million draws from a Poisson, where the lambda parameter, otherwise known as the mu parameter for a Poisson distribution, is being drawn from a gamma distribution with the same number of simulations, shape alpha, rate beta. So we draw from the prior, stick those draws from the prior into the distribution for the data, and simulate data. In this case, a million Super Bowls. And now I can just look at like the histogram for what I think data on the Super Bowls would look like. And so does this look like, you know, a reasonable distribution to you for the number of points that a team would score in a Super Bowl? Maybe. Occasionally you'll see a team score 40. Occasionally you'll see a team get like only 3. That happened in New England like 25 years ago when they played the Bears. But you know, most of the time it's around 20. And in fact, 40 over 2 is 20, which I said was the mean of the gamma distribution. So 20 points for a professional football game is like average. We don't really know if Super Bowls are so distinct from not Super Bowls in professional football. But, you know, a gamma with 40 and 2 might be a reasonable prior belief about mu. And if that's your prior beliefs about mu with that gamma distribution, compounding that with a Poisson, you get something that looks like this. And you know, maybe that looks reasonable to you. Maybe it doesn't. And if it doesn't, you could go back and change alpha and beta until you got a distribution for future data that you thought was plausible. So we're going to get soon, you know, starting Thursday and whatnot, and how to choose priors and all that. And it often seems when you're starting out to be like, I have no idea how I would do that. But you can always sort of express this in terms of a distribution you anticipate the data to be. And, you know, if you choose alpha and beta such that you get a reasonable looking prior predictive distribution, then those alpha and betas are probably fine. Or at least they make sense to you. Mm-hmm.
Does this look normal because you're doing 1 million simulations? This is supposed to be negative binomial, right?
It is negative binomial. It does look normal-ish, but again, the normal distribution is for all real numbers. This one actually stops at 0. This is integers. Can't score a real number of points in football. So it looks normal-ish, but it is not normal. It is negative binomial. Its sample space is the non-negative integers.
Wait, so again, like, are you going to explain the football problem? Sorry, the bowling problem next?
Yes. So you would do the same thing. You would draw from your prior distribution on gamma from the homework, which I said was also a Poisson. Take those draws of gamma, stick them into the Fibonacci thing that tells you the PMF for everything that happens in bowling, and then sample with those probabilities, like 0, 1, 2, 3, 4, 5, 6, up to 10.
Right, you set X as something and then have like sum up over all the gammas.
You don't even really have to sum up over all the gammas in that context. You would need to draw gamma, the gamma parameter from a Poisson that has some mu that you choose. Get like a million draws of that gamma. Figure out the probability in the joint probability table for all million of those for what could happen in 2 rolls in a frame of bowling. And then draw a frame of bowling with those probabilities, except you can make 1,000,000 frames of bowling, each one with a potentially different value of gamma, because you took that from a Poisson. So in order to draw from a predictive distribution, you need to draw twice. Draw a bunch of times from the prior, use those values that you just drew as inputs when you draw from the distribution of the data. And that's how you draw from the predictive distribution. And that will work even if the predictive distribution doesn't have a name. It's just, I drew from the prior, I drew from the PDF of the data.
The X, remember this form of the thing with fx plus 2 over something. So the X is actually the Poisson draw?
No. So draw that gamma thing from a Poisson, like 1,000,000 of those. Draw the first roll of a frame of bowling from its PMF.
I see.
Use that X1, subtract it from 10, draw 1,000,000 second rolls from the conditional PMF for the second roll given the first roll. All that together, you have draws from the prior predictive distribution of bowling pins knocked down.
That's just for that one X.
Yes. So you've used 1,000,000 simulations to tell you what you think for one frame.
It doesn't quite make sense because we're going to predict something. We already have the data. So if you took that first.
Well, no, we don't already have the data yet. So this is prior predictive distribution. So you want to get a simulation that you think is reasonable for future data. So this can be informed by past data. And in fact, I chose 40 and 2 because I knew that 20 was like a reasonable number for the number of points to score in football based on past data. But next year's Super Bowl won't happen for 363 more days. So this is what I believe would be the distribution for the number of points of a team in next year's Super Bowl. But I can use past data to actually estimate mu more precisely, and I can get a posterior distribution on mu and a posterior predictive distribution that is going to be maybe a little bit different from this, even though it'll take the same form. So we got to get rolling on that. So there was a question, why did you choose the gamma? And that's because it's conjugate with the Poisson. So the likelihood function in this case, again, with the likelihood functions, you can drop constants. And by the likelihood function, I mean the likelihood function using the whole sample. So let's say I have n equals 51 Super Bowls that have already been played to have data on. My prior beliefs about mu, again, are distributed gamma with some alpha and beta that you have to choose. And again, there's the PDF for the gamma distribution. So if this is the prior PDF and this is the likelihood, what is the posterior kernel? New. I was looking for a mathematical expression rather than the name of a distribution.
It's sum of what could be exponents of both of them and sum of what's in the mu.
Yeah, so we got mu over here, so alpha minus 1 plus this thing.
Yeah.
And then we got E over here, E over there. This one's got a negative beta, this one's got a negative n.
Sum of that.
We can get rid of that first piece because it only involves alpha and beta, which we've supplied. You can call those 40 and 2 if you want, or some other number. Okay, so the posterior kernel is going to be proportional to mu raised to the power alpha minus 1 plus the sum of the data times E raised to the power minus beta plus n times mu. And if we make the substitutions for alpha star and beta star, we get mu raised to alpha star minus 1, E raised to negative beta star times mu, where alpha star is equal to the original alpha plus the sum of the data, and beta star is equal to the original beta plus n. And if that is our posterior kernel, what is the normalizing constant? What do we have to divide by such that the posterior PDF integrates to 1?
The integral of that.
And what is the integral of that?
It's that gamma, it's that term with, well, I mean, it's beta, which should be substituted by the power, right, the sum, and
Yeah.
gamma.
So it's going to be this thing except the reciprocal and using beta star and alpha star rather than alpha and beta. So that's yet another thing that's a gamma function, with the additional beta raised to the power of beta star raised to the power of alpha star on top of it. So that's that. So this was my prior on mu before I observed 51 Super Bowls. And so it was pretty spread out, but it basically was, only non-zero between 10 and 30. Now, certainly sometimes football teams score less than 10 or more than 30. But this gamma said that I was pretty sure the average for, or the expectation for a team to score in football or a Super Bowl was, between 10 and 30. And, most likely around 20. So again, the red line representing my prior PDF is my prior PDF for mu. And I was pretty sure that that was not going to be like too low or too high. So I had like a reasonably informative prior for mu. And then I actually simulated these Super Bowls, but 51 Super Bowls have actually happened. I didn't bother to get the data on them. But conditional on my 51 simulated Super Bowls, I then got the posterior PDF, which is the blue line there, representing my beliefs after conditioning on these 51 Super Bowls as to what I believe mu is. And now I'm much more sure about mu than I was with my prior. And that typically happens when we condition on data. We get a PDF that's more concentrated than our prior PDF. And so I'm now more sure that the expectation for the number of points the team would score in the Super Bowl is, in the low 20s. There's some chance it could be like 17, 18. But I'm pretty sure what mu is at this point. Now, being pretty sure about mu doesn't make me as sure, I'm less sure about y. Because, even if there's this mu and I don't exactly know what it is, but I'm pretty sure what it is, the y's, the number of points that we observe in football, are still draws from a Poisson. But I'm more sure which Poisson they're being drawn from, because I'm more sure about what mu is, having observed 51 Super Bowls. For some of you, the first Super Bowl you've seen may have been 2 days ago. You didn't know what happened in the previous 51 Super Bowls. The Cowboys won most of them. But, you may have been pretty unsure as to what is like the expected number of points in a Super Bowl. The one that we had just a couple of days ago was a little bit more than average. Yeah.
Is there a way to find out if you were wrong about the Poisson as you do these?
Yes.
iterations?
We haven't talked about it yet, but we'll talk about model checking.
And is there something like a posterior predictor as well? Or
Oh, yeah.
what is that?
We got to talk about some frequentist crap for a second. All right. So a maximum likelihood estimate is obtained by coming up with an estimator mu that maximizes the likelihood function. So ignoring the prior, or not ignoring, but never acknowledging that the prior is a thing, and the denominator of base rule, the constant, none of that is taken into consideration. We're just talking about the likelihood, by which I mean the log likelihood. And we're going to choose some mu hat in order to make this log likelihood function as tall as possible. And since the log likelihood is a monotonic function of the likelihood, if we make the log likelihood as tall as possible, we make the likelihood as tall as possible as well. So the likelihood, the log likelihood function, if you take the logarithm of the Poisson PMF and then accumulate it up overall in observations you have negative n times your estimator for mu times the logarithm of mu multiplied by the sum of the data. All right? And how do we choose mu to maximize a function? Differentiate with respect to mu and set it equal to 0. So the derivative of negative n times mu is negative n. The derivative of log u of mu is 1 over mu, and then there's the sum of the data there. Set that all equal to 0. Rearrange it. We find in this case the maximum likelihood estimator of mu is the sample average of y, typically known as y bar. All right. So hopefully you get the sense that being frequentist is a lot easier than being Bayesian. You don't really have to manipulate around like 3 distributions at once. You don't have to do any integrals or not do any integrals, as the case may be. All you have to do is take a derivative and then solve an equation or system of equations. The system of equations can get a little tedious. But if you only have one parameter, then there's only one equation in your system. Technically speaking, I should do the second derivative and check that this is a maximum rather than a minimum, but we never really do that. Likelihood functions are well behaved enough that you get maxima rather than minima or stationary points in simple problems like this. Not always. Simple problems like this. So fun fact about the Poisson distribution is that if you sum up n random variables that are Poisson distributed with mean mu, you get another Poisson. Its expectation is n times mu, and Poisson, as its expectation goes to infinity, approaches a normal distribution. You may have heard of that before. Even though it's discrete, it sort of as the expectation gets bigger and bigger, it has the sort of normal shape to it. It converges to a normal. So the asymptotic distribution of the sample mean estimator, asymptotic means as n goes to infinity. So the sample mean estimator is just going to be this Poisson, or this, the distribution of the sum, which is Poisson with expectation n over mu. The sample mean is just Poisson, or the same thing except dividing by n. So the n's cancel. And what we're left with is something that converges to a normal distribution with mean n times mu divided by n, or just mu. And since the Poisson, its variance is equal to its expectation, so the variance of the sum is also equal to n times mu. But when we divide for the averaging process, then the variance is scaled down by a factor of 1 over n squared. So the n in the numerator cancels with one of the n's in the denominator. And so the variance of the normal distribution that this thing is converging to is mu over n. And this is just a special case of something known as the central limit theorem, which frequentists are very proud of themselves for discovering. Basically, any estimator that has a finite expectation and a finite variance is going to, or the mean of any distribution that has sample mean of any distribution that has a finite expectation and finite variance, the sample mean is going to be distributed normal with expectation equal to the mean of the data generating process and variance equal to like the variance of the data generating process divided by n. So doing the averaging reduces the variance by this factor of 1 over n. And this is not just the case for Poisson, it's true very generally. But this is a special case of this. So we have an estimator, and that estimator is asymptotically normal with mu and variance mu over n. So it is true that before you sample n observations even once, it is quite reasonable for you to anticipate that the sample mean will be within 1.96 standard deviations, standard deviation being the square root of the variance, variance being mu over n. Perfectly reasonable for you to anticipate the sample mean will be within, minus or plus of that thing of mu. And you can use that with probability 0.95. So you have a 95% chance that the sample mean will fall within plus or minus 1.96 standard deviations from the mean with probability 0.95. So you can use that information to choose how big of an n you need, presuming you're the one who's actually choosing the n. So if you need it to be, sufficiently close to mu with a sufficiently high probability, you can choose the n to make that happen. And this is really like the essence of how frequentism was invented or first started out, like between World War I and World War II. They were interested in questions like this. How big an n do I need to get my estimator to be, expected to be sufficiently close to the true population mean with sufficiently high probability? And can I afford such an n? These days, particularly if you're not doing primary data collection, you're just doing secondary analysis, you don't choose your n. However the n came to be, it probably wasn't that expensive. So this is like a less critical question than it was 80 years ago. But in a manner of speaking, this provides you a way to answer that question that like your great-grandparents might have asked themselves. So it's an answer to a question that's not completely silly and actually used to be real important, and now it's just like kind of important in some cases, but often not so much because data is cheap. All right. So how would you choose n?
That expression should be greater than 0.95.
Yeah, so there's a 0.95 that's going to be in this interval. And so you can plug in different values of n, but that wouldn't tell you the width of the interval. You need one more piece of information. I need a what? You haven't collected the data yet, so you don't have a sample mean. You know n, you don't know y bar yet because you haven't collected n observations yet. You're trying to figure out what n you need. What's the only other unknown in this expression? Right. So although this whole frequentist thing was cooked up to answer questions, how big an n do you need? You can't really answer that question unless you have some sort of a belief about mu. Except frequentists don't want to talk about what are your beliefs about mu. Because if this just becomes what do you believe, then frequentism is not constructed to answer that question. The infidel is. All right. Yes.
If you had a belief on mu,
Uh-huh.
you could pick a mu to maximize the posterior of mu, right? The posterior distribution of mu.
No, not posterior distribution because you need data for that. I mean,
Suppose you have this one set of data.
oh, you already have data.
Yeah.
Well, then you should just condition on that data, use whatever seems like a reasonable prior for mu, and then get the posterior distribution on mu conditional on that data. But that doesn't exactly answer the question like, how much data should I get?
Yeah, it's not related to the n. But what my question is, would the mu that would give, would that be better than the mu to get through this sort of
No.
this likelihood?
Like you want the posterior, maybe the expectation, maybe the posterior median of mu. One of those things. You don't want to be like choosing mu. You want to just condition on the data and accept the posterior distribution. You choose your prior, but you don't choose mu. All right, so comparison. If you do the gamma Poisson Bayesian thing after you get in observations, however you came to arrive at n. So first thing, this is what a lot of frequentists mess up in practice. After it's okay, so this is reasonable. The bottom thing. Well, it's correct. I don't know how reasonable it is, but it is true that you should anticipate before you get the data that the sample mean will be within 1.96 of the square root of mu divided by n. You don't know what mu is, but mathematically, this is like a coherent thing. What frequentists mangle it into is after you sample in observations and you actually construct the sample mean y bar to say there's a 0.95 probability that mu falls within the interval y bar minus or plus 1.96 times the square root of y bar over n. So just plugging in y bar for mu and then saying like whatever, it used to be 0.95, now I'm switching mu and y bar is still 0.95. And that's false. That's what people are trying to do with a confidence interval, but that it doesn't make sense under frequentism or under Bayesianism. The frequentist probability statements are all pre-data. This thing in the bottom here. Post-data, there is no frequentist probability. Y bar or mu either is within that interval or it's not. You don't know which, but you can't make a probabilistic statement about mu because mu is conceived of as a constant rather than a random variable. You can only make probability statements about random variables, which mu is not among them. The estimator is the random variable, technically speaking, for frequentists, but applied frequentists want to use the estimator and then make a probabilistic statement about a hypothesis or about a parameter. And that's like tolerated by frequentists, but it doesn't follow from the frequentist assumptions about probabilities being like long run proportions. And it certainly doesn't follow from Bayesian theory. However, in this case, with a gamma prior and a Poisson PMF for the data, you get this posterior, which was also gamma with parameters alpha star and beta star. The posterior mode for a gamma distribution is -1 plus alpha star divided by beta star. And you can plug in alpha and beta there for alpha star and beta star, what those are equal to. The posterior expectation, U star, is equal to alpha star divided by beta star. And the posterior variance is equal to mu star divided by beta star. So if and only if, so this is an extraordinarily special case, your prior beliefs are such that alpha is 1 and you let beta approach 0 from above. So these are your prior hyperparameters, alpha and beta, not alpha star and beta star. So you choose alpha equal 1 and you let beta go towards 0 from above. The posterior mode here, if alpha is 1, then the -1 and the 1 cancel. And your beta approaches 0, so you just have n in the denominator. In that case, the posterior mode for that Bayesian coincides with the maximum likelihood estimator of mu, that being y bar. They're always different concepts, but there are prior beliefs in which the posterior mode and the maximum likelihood estimator are the same number in this case. Also, if you have those beliefs, the variance of the posterior distribution is going to be asymptotically equal to the asymptotic variance of the maximum likelihood estimator y bar over n, or the estimated variance. So what we're saying here is that the mode and the variance of the posterior distribution of this Bayesian who came in believing this is sort of asymptotically, it's the same normal distribution for the frequentist, where the frequentist is talking not about a posterior distribution, but the distribution if I collected data, calculated the sample mean, collected another set of data of the same size, calculated the mean, collected another data of size n, calculated the mean, did that over and over and over again. The distribution of that guy's sample means is going to be normal with, you know, mu and variance mu over n. And, you know, the posterior distribution is going to have that same variance. So there are situations in which those distributions can coincide. It doesn't mean they're the same number. Or just because they're the same number doesn't mean they're the same concept. And you always have to remember that, you know, your frequentist textbooks, if you like read them very carefully, they never assert that you should actually believe mu is y bar. And when I point that out to people, they are often like, now that you point that out, I don't recall my frequentist textbook telling me I should believe mu is y bar. They can't say that. That would be wrong, or it wouldn't follow from their assumptions. However, under these specific conditions, there's going to be negligible cost to misinterpreting the frequentist sampling distribution that comes from their central limit theorem as a gamma distribution with parameters alpha star and beta star if you started out believing alpha is 1, beta is 0, and you had a large n. So they're not the same thing, but those two distributions can get like eclipse of the sun, under particular conditions. Now, those conditions are pretty specific. So just because, you know, you could get these things to line up with each other doesn't mean that you should believe alpha equal 1 as beta equals 0 if you're trying to formulate your prior beliefs about the expectation of the number of points scored by a team in the Super Bowl. Like the expectation of that would be 1 over 0. So you're saying you expect, you know, one of the teams in the Super Bowl to score an infinite number of points in a finite amount of time. Like that is a stupid thing to believe about the Super Bowl. But that's what you have to believe in order for the maximum likelihood estimate to be the same as the posterior mode. It's also stupid to believe that you have an infinite number of observations. In the actual thing, you're going to have a finite number of observations. And so you might think, well, okay, if the Bayesian thing is sort of, you know, appropriate for finite n and the frequentist thing is sort of appropriate as n goes to infinity, then in any practical application, you're going to want to use the Bayesian thing rather than the frequentist thing, which is talking about you having more data than you do. But moreover, as we were talking about on the first day, this that we got here was based on the posterior mode coinciding with the maximum likelihood estimator. And the posterior mode is also a stupid thing to believe. It's optimal if your loss function is equal to 0, if your estimator is exactly equal to mu, and your loss function is equal to 1 if your estimator is in any way different from mu, like even in the millionth decimal place. So your loss doesn't depend on like how far away your estimator is from the thing that you're estimating. It just has to be like different. So you're never going to achieve that anyway. So it's sort of useless to choose a point estimator to minimize that loss function. You're usually going to be much better off with the posterior mean or the posterior median, which, you know, minimize squared error loss or absolute value of error loss respectively. If you have to believe one number, if you have to make a decision based on, you know, what you believe in terms of one number, then the decisions you make based off the posterior mean or the posterior median are going to be, more reasonable decisions, or decisions based on a more reasonable loss function than decisions based on the posterior mode, which are based on a completely unreasonable loss function. So the posterior mode is a real red herring. Prior mode can sometimes be kind of interesting, but once you condition on the data, you really don't want to be worried about modes anymore. But that's what corresponds most directly-ish to what frequentist estimates give you under some like asymptotic circumstances. All right, so we ran out of time. I have one more slide about posterior predictive distribution, but it's pretty much the same thing as prior predictive distribution, except you stick in the posterior rather than the prior, and then draw what you believe future data to look like. Okay? So see you Thursday. Also, look on Piazza. We may likely have a review session this Friday. It'll be optional. We'll try to tape it if you can't be there. But we might have one if I can get a room Friday, probably late afternoon. Yeah. Let me turn this off first.